Let us examine a set of experiments conducted in 1949 by L.S. Darken. The experiments were carried out with two bars of steel that are brought into contact with each other. On the left side, we have the composition of 0.48% carbon, 3.8% silicon, and the remainder iron. The right hand side, the bar contains 0.45% carbon, practically the same as in the left bar. Significantly lower amount of silicon, 0.05%, and the remainder iron. The two bars are raised to a temperature of 1323 Kelvin by placing them in a furnace for 13 days, and thereafter the bars are quenched and the compositions of carbon along the distance from the interface measured on both sides. We note that the diffusion profile or the concentration profile for carbon exhibits a minimum, and then it increases near the surface and then decreases to the value that is equal to the initial value. So in this region, the carbon atoms experience uphill diffusion from a low concentration of carbon to a high concentration of carbon. This is a technique used for surface hardening because the surface now contains a higher portion of carbon and is harder than the bulk that is tougher. So carburization using this technique involves exploitation of the principle of uphill diffusion. Let us examine the Darken experiments in a little bit more detail. The addition of silicon to the left compartment or the left bar increases the escaping tendency of carbon and therefore influences the activity. The activity of carbon in the mixture of carbon, silicon, and iron is a function of both the weight percent silicon and the weight percent carbon. For a given weight percent carbon, the addition of silicon increases the activity of carbon. If we replot the experimental data in terms of the activity against the distance from the weld interface, we note that the activity progresses monotonously from a high activity region to a low activity region and does not show any minimum or maximum. In other words, the experience of uphill diffusion is not observed when we use activity gradients as driving forces for transfer of carbon from one compartment to the other. On the basis of his experiments, Lawrence Stamper Darken drew the following set of conclusions that also serve as takeaways for this presentation. Firstly, the driving force in an isothermal diffusion process may be regarded as the gradient of the chemical potential. For a system with more than two components, it is no longer necessarily true that a given element tends to diffuse toward a region of lower concentration even within a single phase region. The word single phase is quite important, as we shall see later. The departure from the behavior of an ideal solution may be so great that the concentration gradient and the chemical potential gradient or activity gradient may be of different sign, thus giving rise to uphill diffusion.